All right, in my last video, we talked about the classical harmonic oscillator. And in this video, I'm going to start talking about the quantum harmonic oscillator, or the quantum HO, as it's lovingly known. The process for doing this is the same as all of our problems in quantum. Write the Schrodinger equation, solve it, and interpret it. And so away we go. We're going to write the Schrodinger equation. It starts like this. H psi equals E psi. H is the Hamiltonian operator. Right? E is the observable, the total energy. When I think about the components then of the total energy, there's a kinetic energy term. This looks like it often looks. And then unique to this case, or new to this case, is a kinetic energy term. Right? Remember, I think I said kinetic energy, but I meant potential. Potential energies for harmonic oscillators are 1/2 kx squared. And so the quantum mechanical operator is 1/2 kx squared. When I add that into my Hamiltonian, I will get a term which looks like this. So second derivative with respect to position is a kinetic energy. This is the potential energy. Total energy is the eigenvalue. All right, at this point, we need to solve this equation. We need to do step 2. And remember, when we solve the Schrodinger equation, we get two things. We get wave functions and energies. And this is a linear algebra problem. I'm not going to go through it at this point. It's beyond the scope of what we need to know for this class. You can see some of the notes that are up in Macquarie or up on Canvas for some details on how to do it. But this is the result. Okay. Here are the harmonic oscillator wave functions, which satisfy the Schrodinger equation. Psi of x is equal to n sub v h sub v e to the minus y squared on 2, where quantities have lots of definitions. So y is defined as follows: x over alpha. Alpha is h bar squared over mk to the 1/4. And v is some number, a counting number. 0, 1, 2, 3, dot, 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 dot. So there's an awful lot going on here, and I want to sort of parse through this. I'm going to go big picture first. So if you look at the solution, the wave functions, there's actually 3 parts. The first part is right here, this n, which is simply a normalization constant. This is adjusting the height of the wave function so that when I integrate it over all space, I get a probability equal to 1. The second part is this h sub v of y. And this is a polynomial. Okay, this is a simple polynomial. And the way that you read this, right, is h, the polynomial, as a function of the variable y. We're not multiplying it by y, but h, our polynomial, is a function of this variable y. And last but not least is this term here. This is a bell curve, right? So this is this Gaussian bell curve. So big picture, those are the 3 parts to this. Now let me start getting into some details. The first is that you'll notice that this is labeled with a subscript v. V is a quantum number, right? It's a counting number, 0, 1, 2, 3, whatever. We refer to this as the vibrational quantum number. And just like the particle in a box, where we require the wave function to go to 0 at the edges of the box, or the potential, in this case, when x is equal to plus or minus infinity, the potential is infinite. 1/2 kx squared. So if I have an infinite position, I get an infinite potential. That requires that the wave function go to 0 and imposes this quantized boundary condition. Right? That's where this comes from. So all of these solutions are labeled by the quantum number V. The other thing that you might be asking is, well, what in the world is this variable y? And what it is something called a reduced variable. Y is a way of describing the position of a particle. So y is proportional to x. But it's written as a dimensionless quantity to simplify the mathematical form of this. So it's a way to sort of simplify our mathematical notation. And I'll talk a little bit more about that here in a second. So let's dig into these parts. This is the normalization constant, n sub v. The first thing that I point out to you is that you will note that there's a subscript v associated with each quantum number n. In other words, different wave functions will have different normalization constants. And you can calculate what this normalization constant should be, and this is the formula that you end up with. Written in a couple different ways. I think this one's a little bit easiest. So that's the formula. And one quick note here on notation, you'll note that there's an exclamation point. That's not a typo. It's a mathematical symbol called a factorial. Factorials are defined as follows. N factorial is n times n minus 1 times n minus 2, dot, 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 all the way down to 1. So 3 factorial is 3 times 2 times 1 is equal to 6. 2 factorial, 2 times 1. Dot, 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 dot. Note that vibrational quantum number, V, started at 0. So you could have a situation where you have 0 factorial. And I'm not going to tell you what 0 factorial is, but you can Google it and see some cool math videos and figure out what it is. Anyways, that's the normalization constant. The second thing to talk about are our polynomials, h sub v. So these polynomials have a specific name. They're called Hermite polynomials. And they were derived by a famous mathematician, Hermite. And at this point, we can consider them simply to be tabulated polynomials. Right? You can look them up in a book, and they're in Atkins. I will post a handout to Canvas that has all of this information. You can find it here. And I've listed them here, right? So these are the different Hermite polynomials for different quantum numbers V. So h sub 0 is simply 1. It's a constant. H sub 1 is 2y. Looks like this. H sub 2 is 4y squared minus 2. It's the blue one. So these are simply tabulated polynomials that you can look up in a book. Now, they're famous. Right? They solve some important famous math problems. And Hermite polynomials have some relevant mathematical properties that you should know about. The first is that they have a specific symmetry. Right? Hermite polynomials are odd or even. And what I hope you might be able to convince yourself looking at these is that the h sub v, where the v is odd, 1, 3, 5, are odd polynomials. Right? Here's h sub 1. You can see it has inversion symmetry. It's an odd. Whereas h sub v being even, 0, 2, 4, right, are even functions. So they have the mirror plane. So Hermite polynomials have a specific symmetry. The integrated areas between Hermite polynomials obey certain relationships. Right? That is, if I were to multiply two Hermite polynomials and this Gaussian factor, you get these answers. Right? If the Hermite polynomial is the same, you get some finite number. But if the Hermite polynomial is different, if v prime is not equal to v, you get 0. And just a couple quick comments about that. That might make some sense to you. Remember that wave functions, eigenfunctions of Hermitian operators are orthogonal. Right? So if I have two different wave functions, they don't overlap. And the other way that this might connect with you is this notion of odd-even symmetry. Right? So this hopefully makes some sense to you. Last but not least, there are a series of what are called recursion relationships, which relate polynomials. Recursion relationships are essentially algorithms that tell you how they're generated, how one relates to the other. And I've written them here, they're on the handout and you can check these things out, but this will ultimately end up being helpful for calculating various properties that are associated with Hermite polynomials. All right, that's all I want to say about the h sub v. The last function I want to talk about then is the Gaussian curve, e to the minus y squared on 2. And this is a kind of plot that you should be familiar with. You know, exponentials, sine, cosines, you should know bell curves. I've shown one here. These are what some people think grade distributions look like. They're all straightforward. They go to 0 at x equals infinity. And what I would ultimately tell you here is that you might buy then that the width of this curve, right, is related to y, and that y itself is related to alpha. So alpha, this reducing constant, is related to the width of the curve. It's telling you something about how much this system is oscillating. Those are the components of the wave function. When you put it all together at the end of the day, here's what you get. Here are the harmonic oscillator, the quantum Ho wave functions for v equals 0, 1, 2, 3, 10, ta, 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 ta. On the right, I've squared these and you can get the probability distributions, psi squared. So we should just take a second and interpret these a bit. That's sort of our third step. Question I'm asking is, what do we notice about the wave functions? And let me point out a couple things to you. So the first is nodes. Right? You'll see that the lowest harmonic oscillator wave function, v equals 0, has no nodes. V equals 1 has 1 node. V equals 2 has 2 nodes. Right? So v, the quantum number, is telling you the number of nodes in the system. And as you might anticipate, as the number of nodes goes up, the wave function's decreasing, and we might expect that energy is going to go up. The second thing you might notice about these is that, in fact, they look a lot like the particle in a box wave functions. The lowest energy particle in a box wave function was a sine curve. The second one was one whole sine revolution. Third one was 3 sine revolutions. So these look a lot like the particle in a box wave functions, with one notable difference. I told you, which is at the edges of the box. Particle in a box wave functions were sine curves, so they abruptly went to 0. Whereas the particle in a box wave functions look a little softer at the edges. Right? You'll notice that this is sort of slowly decaying to 0. And so why is that? Well, remember that in a harmonic oscillator, the potential is slowly increasing. Actually, let's do this. So if I have a particle in a box, right, it looks like this. The potential does. Whereas if I have the harmonic oscillator, it much more slowly increases. So the wave function is going to gradually decrease and ultimately produces the same type of shape, but softer at the edges. You should be able to sketch harmonic oscillator wave functions if I tell you a quantum number. Right? Sketch V equals 1. You should be able to do that. The last thing I'd point out to you is that there is, in fact, some sort of weird behavior here. So we said in the previous video that classical harmonic oscillators hang out at the turning points. They slow down and they spend their time here. They move very quickly through the origin. Look at this one. This is a quantum harmonic oscillator. What is it doing? Well, it's hanging out in the middle, right? X equals 0. And it has a low probability of hanging out at the turning points. It's the exact opposite of a classical harmonic oscillator. It's totally weird. But in fact, as you start to increase the energy of the system, right, as you start to increase the quantum number, you get something like this, V equals 10. And if you start to look at V equals 10, you'll notice that psi squared is much bigger at the edges than it is at V equals 0. So at high quantum number, it hangs out at the edges and less in the middle. It looks like a classical system. And in fact, this has a specific name. This idea is called the correspondence principle. I wrote a mathematical version of it there. The limit as n approaches infinity of quantum mechanics is equal to classical mechanics. So as I increase the quantum number, I start to approach classical behavior. And this was a plot from Atkins, which I think sort of nicely illustrated that idea. I will stop here, and in the next video, I will talk about energies. See you then.